Worked problems for chapter 9. So these are going to be dealing with VSEPR, valence bond theory, and so forth. And there's a few in here about molecular orbital theory, so we'll get to those. So I want to give credit at the beginning here. Basically, these are my slides, so I put copyright on them, but the problems are taken mainly, I think, from Zumdahl, and some taken from Brown and LeMay, occasionally one from McMurray. And then there are also usually a few multiple choices that I took from Mr. Max AP chemistry site. Next slide. So here are your sources: McMurray chemistry, Zumdahl chemistry, and Brown and LeMay chemistry. Next slide. And then I'm the one that provided the solutions. Next slide. All right, number one, what are the key differences between valence bond theory and the VSEPR model? So let's start with the VSEPR model. The main point of that is that you're counting how many charge clouds you have around a central atom. Is it 2, 3, 4, 5, or 6? And then you try to get these charge clouds as far apart as possible. In other words, if you have 2, the way they can get as far apart as possible is to be in a straight line. On the other hand, valence bond theory is dealing with looking at the bonds and determining whether the bonds between two atoms are sigma bonds or pi bonds or both. So sigma bonds can form between two s orbitals that are in atoms, or they can also actually form between two p orbitals as long as they're the ones that are directed along the line between the two atomic nuclei. So sigma bonds are direct bonds that go directly between the two nuclei, while pi bonds are going to go either above or and below the sigma bond, or to the left and to the right. So there are different kinds of bonds. So valence bond theory looks at what kind of bond hybrid will form. It contemplates the existence of hybrid bonds that are neither S nor P, that are some kind of, as it were, a hybrid between S and P. And there are several different kinds. So depending on what the molecular shape is and how many charge clouds there are, that will determine what hybridization they will have. Let's go to the next slide. So valence bond theory says that the greater the overlap there is between bonds, the stronger the bond will be. Let's go to the next slide. All right, so I think we'll have time to go through this. So here's a review. So what I'm going to do is go through this kind of quickly because we did it in the lecture notes. So whenever you have two things around a central atom, as we see at the top here, and let me get my marker turned on. So as we see right here, when you have two things around a central atom, you're going to have a linear electronic geometry always, and the shape will be linear if both of the charge clouds are atoms. So this is just harkening back to what we said in the lecture notes for this chapter. So in this case, usually that's the only way you're going to see it. When you have three charge clouds, the electronic geometry will always be trigonal planar. If you replace one of the atoms with a lone pair, then it becomes a bent shape, but that's not the electronic geometry. The electronic geometry here is still trigonal planar, okay? It's because you have three charge clouds and they're spread out as far as they can get, 120 degrees between each one in one plane. So it's planar because these things are in one plane, and it's trigonal because there are three charge clouds in that arrangement. But if you remove one of the atoms, as we've done here, we've replaced this atom here with a lone pair here, then we no longer have a shape of the molecule that's trigonal planar. It's now bent. So, but if they asked for the electronic geometry of this, it would still be trigonal planar because you would count the lone pair for that one, but you don't count it for the molecular shape. Now, it's a little more confusing because they're calling this thing the molecular geometry. So what I'm calling this is not the molecular geometry. It's called I'm calling it the molecular shape. And I'm not going to try to write this out because it's hard to write with this thing, but SHAPE, molecular shape. So we're going to talk about two things, either the electronic geometry or the molecular shape. All right, so let's come down here now to 4. If you have 4 charge clouds, the electronic geometry is always going to be tetrahedral, but the molecular shape can vary depending on whether these are all atoms. So here in this top one, we have all atoms, 4 of them. So the molecular shape is also tetrahedral, but Here we've replaced one atom with a lone pair. So again, the electronic geometry is still tetrahedral, but the molecular shape here is trigonopyramidal. So it's trigonal because we have 1, 2, 3 things around the base, and it's pyramidal because it makes a little pyramid. If we take another atom off and replace it with a lone pair, as we've done here, then we still have tetrahedral electronic geometry, but our shape of our molecule is bent. Next slide. When you have 5 charge clouds, if they're all atoms, well, the electronic geometry will always be trigonobipyramidal, which is because we have a pyramid here on the top that points up, and then we have another one that has the same 3 for its base, but it points down. So there's 2 pyramids. Each of them has a base with 3, so they're 2 trigonal pyramids, so we call it trigonobipyramidal. For all of these, all 1, 2, 3, 4 of these possibilities, the electronic geometry is going to be the same because you're still going to have 5 charge clouds. So the difference is whether they're lone pairs or atoms. So if they're all atoms, then the molecular shape will also be trigonobipyramidal. Now remember, as we said in the lecture notes, when you're doing 5, then you remove from around the middle here, like these 3, these equatorial positions. So first of all, if we remove this one right here, then and replace it with a lone pair, then we have still electronic geometry of trigonobipyramidal. But because we removed an atom and replaced it with a lone pair, the molecular shape is no longer trigonobipyramidal, it's a seesaw. If we remove a second one, so now we've removed 2 atoms replaced with lone pairs, now we have a T-shape for the molecular shape. Again, but for all of these, the electronic geometry will still be the same. And then if we remove all 3 of the ones around the middle, we only have now the one on the top here and the one on the bottom here. So we have a linear shape like this. So the molecular shape is linear, but the electronic geometry is still trigonobipyramidal. Okay, I should have probably started to do this earlier, but when you have 5 charge clouds, you want your exponents in terms of your valence bond theory. Valence bond theory gives you different possibilities like sp3, sp2sp, dsp3, and d2sp3. So you want your exponents to add up to the number of charge clouds. So here we have 5 charge clouds, so we want exponents in the ds and p that add up to 5. And the way that would happen would be if you had d, s, p3. So you can think of the d as having an exponent of 1. The s also is 1, and the p is 3. So 1 plus 1 plus 3 is 5. So whenever you've got this electronic arrangement like this, then you've got dsp3 hybridization and valence bond theory. So I can back up a little bit. When you have 4, it would be sp3, that's s1p3, 1 plus 3 is 4. When you have 3, you have sp2, s1p2, 1 plus 2 is 3. And when you have 2 charge clouds or it's linear, you just have sp. Let's go to the next slide. And then the last one here, 6, which is not as hard. You just have to remember when you have 6, you remove from the top and the bottom, not around the middle. And I mean, it seems silly to say this, but if you can't remember that, then you're going to get totally confused. So when you have 6 charge clouds, the electronic geometry will always be octahedral. But the molecular shape will depend on how many of those charge clouds are atoms and how many are lone pair. If they're all atoms, as we have here, then the molecular shape will also be octahedral. But if we remove, for example, the bottom one here and replace it with a lone pair, now we have just this thing here that's left over, which is a pyramid with a square base, so we call it square pyramidal. If we remove the top one now here, then now we have something that's in a plane and it's square, so we call the molecular shape square planar. But the electronic geometry is still octahedral, okay? Because over here, look to the right here, for this one we still have 6 charge clouds, and that means we have an octahedral electronic geometry. So email if you don't understand this, please. Next slide. Okay, Mr. Mack's website. So this is a good place to go if you want to get some extra practice. So this one says the molecular shape which I'm going to just, if you'll bear with me for 1 second, I'm just going to mark that out, and I'm going to underline up here where it says shape. The molecular shape of blank is square planar. Now, you can save yourself some serious time on this problem by just stopping and thinking about what do they mean by molecular shape. So we're not talking about the electronic geometry here. We're not talking about lone pairs. We're just talking about atoms. So in order to have square planar, you've got to have one thing in the middle, which I'll try to draw this. It's really hard with this thing. And then you've got 1, 2, 3, 4 atoms. 1, 2, 3, 4 atoms around the central atom, like that. So what that means is that you would have to have 4 atoms. Now this is one of the very few places that you can take a kind of a shortcut without taking a chance on getting it wrong, because that means that these 3 choices over here are going to be wrong, because they don't have enough atoms to make a square planar arrangement, because there's only 3 here, and there's only 2 here, and there's only 3 here. So look back at A and B. They both have 4 things around a central atom, so they could both be right. However, so let's quickly do the Lewis dot structures. I'm not going to draw them out because I can't with this, but let's count our electrons for A and B. So for A, we've got 4 for carbon and 7 for chlorine, times 4 would be 28, plus 4 for the carbon would be 32 total electrons, and we would use 8 of those 32 to make the 4 bonds between the C and the 4 Cls. So 32 minus 8 would be 24, and so we would then take those 24 electrons, and 6 would go on each chlorine, and that goes perfectly. 4 times 6 is 24, so we would use up all the remaining electrons on the Cls. That means there's no lone pairs left to go on the carbon in the middle. So that is going to wind up with 4 charge clouds, because there's nothing left over to make a lone pair there. So, I mean, if you don't see exactly what I'm saying here, just look at it a few times. We're going to wind up with a carbon with 4 chlorines around it, so that has 4 charge clouds, and the way they can get farthest apart is a tetrahedral geometry for the electrons and also for the atoms. So it's going to be tetrahedral, not what they're asking for in this problem, which is square planar. So it will have a tetrahedral, both the electronic geometry and the molecular shape, and the angles will be 109.5, and the hybridization will be sp3, s1p3, 1 plus 3 is 4, 4 charge clouds. So, but this is not going to be the answer, because this is going to be tetrahedral. Come over to B. Xenon has 8 valence electrons and F has 7. So 7 times 4 is 28, and 28 plus 8 is 36, and we'll use 8 in the 4 bonds, so that leaves 28 electrons, and we can put 4 times 6 is 24 on the F's, which leaves 4 electrons. So that means that we're going to have to put 2 lone pairs on the central xenon here, one there going up and one coming down, like this, and then we still have these 4 bonds to these 4 atoms. So that means we have a total of how many charge clouds? Well, 4 bonds to atoms and then 2 lone pairs. 4 plus 2 is 6. So that means we're going to have an octahedral, and I'm just going to write O here if I can. O for, that's going to be for the electronic geometry. It's super hard to do this, and especially if you want to try to make it look good. And then the molecular shape will not include this lone pair or this lone pair. It will only include the 4 atoms. And so because this is octahedral in terms of its electronic geometry, then it's going to wind up with these 4 things here being in one plane as a square. I'll show you a better picture of that on the next slide. So the molecular shape here would be square planar. Now, if you want to come over to C and just play around with it, or D or E, iodine is 7 and chlorine is 7, so that's 4 times 7 is 28 electrons to work with, of which 6 would be used on the 3 bonds, which leaves 22. And then you can put 18 of the 22 that are left over on the chlorines. You still have 4 left. That's 2 lone pairs on the I. So you've got 2 lone pairs on the I, and then you've got 1 chlorine above, 1 chlorine below, and 1 chlorine to the right. And I mean, you won't be able to do this in your head. You'll have to do this on paper. And in this particular case, you wouldn't have to do it because you've already eliminated this one. But some problems you may have to do it for all 5 choices. And you should do that, because if you don't, you'll almost guaranteed get it wrong. But that's going to wind up with an electronic geometry of trigonal bipyramidal and a molecular shape that's going to be T-shaped. And you could do the same thing for this one and the same thing for this one. So what you'll have to try to get good at is remembering how many valence electrons do the things in these problems have. Anything in the 7th column has 7, so that's fluorine, chlorine, iodine, and bromine. Xenon is actually in the 8th column, so it would have 8. Let's see, and that one is also over here. All right, so anyway, so our answer is going to be B, so let's go to the next slide. And here is actually the picture of what this would look like. This is a better picture, obviously, and the fluorines all have 3 lone pairs. So we used 6, 12, 18, 24, 26 up here, and 28 down here. So we used all of our electrons. We have 6 charge clouds. So we have an octahedral electronic geometry, and that means that we're going to have D2, and I'll try to write this. I'm only writing this because we don't have that much to do. sp3. 2 plus 1 for the S plus 3 for the P is 2 plus 1 plus 3 is 6. And that matches here, right? So this would be the valence bond hybridization for this kind of a molecule. It would be D2sp3. Now, I know they didn't ask that, but we'll get to that. Okay, next slide. All right, here's BrO3. So we're going to have a Br in the middle, and we're going to put O's around it for now. So put an O there, an O there, and an O there for now. Let's count our electrons. So that's 7, and O's have 6 times 3 is 18. That's 25, and then add 1 for the minus charge. So we have 26 valence electrons, and we're going to be able to use 6 of those in our bond to each of the O's. So that uses 6. 26 minus 6 would leave 20, and then we put 6 of those on the 3 O's, and that will use up 18, leaving 2 left over that have to go on the bromine. So we're going to end up here with a lone pair on the bromine and then 3 bonds around it. So now, how many charge clouds total do we have around the bromine? We have 1 lone pair here, and then we have 3 atoms. Total of what? 4. So 4 charge clouds. We've got sp3 hybridization, s1, p3, 1 plus 3 is 4, and then it's going to have a tetrahedral electronic geometry. So the electronic geometry will be tetrahedral, which I'm trying to do this quickly. The molecular shape, though, will not be tetrahedral, because the molecule only contains the Br and the O. So that actually would be just this part here at the bottom. It wouldn't include the lone pair. And that would be in the shape of a pyramid. So it's going to be pyramidal, and it's got a base of 3, so it's trigonal pyramidal. And let's go to the next slide and look at a picture. And so this is what this would actually look like. So this is not showing, but we have a lone pair up here, right? It's just not that they're not showing that, but the molecular shape you can clearly see here is a pyramid with 3 at the base, so it's trigonal pyramidal. So the answer is going to be B here. Next slide. 5, according to the SEPR theory, if there are 5 electron domains in the valence shell, they will be arranged in. So 5, so 4 was tetrahedral. What about 5? Can you remember what 5 was? Tetrahedral. 5 is trigonal bipyramidal, right? So TP. And what was 6? I mean, they're not asking, but it's actually supposed to be trigonal bipyramidal. Okay. 6 would be what? 6 would be octahedral. So anyway, what's the answer here? It's E, right? Trigonal bipyramidal. And we're talking about the electronic geometry. Next slide. So, I mean, this may seem a little bit difficult to you, but it actually isn't. So I recommend very strongly that you try to go through these work problems like 3 times minimum. They should, I mean, by the time you go through it the 3rd time, you should be able to just flip through them. And then if you have time, I would go to Mr. Mac's website or something and just get some more practice, or just make up your own problems. Anyway, next slide. So give highlights of sp3, sp2, and sp hybridization. So this is valence bond theory, first of all. sp3 is the easiest one to start with. We have in carbon, for example, it could also be oxygen or nitrogen. We have either 4 or 5 or 6, depending on which one you choose. So let's choose carbon. So you have 4 valence electrons. That means in the 2 shell, you have 4 electrons. 2 are s, 2 are p. So remember, we went through the little spiel where one of the s's goes up to the vacant p, and then the s goes up quite a bit, the p's come down a little bit, and you wind up with 4 hybrid orbitals that are all at the same energy level. So they're called sp3 because they started from 1 s orbital and 3 p orbitals. They all wind up being the same, so you end up with 4 charge clouds, and you wind up with all single bonds. They're all arranged at 109.5 degrees. And they will wind up making a tetrahedral shape. For sp2, it kind of goes the same way until you get to the point where you bring down the p's and raise up the s orbital. And in sp2, you don't bring down all 3 of the p's, you just bring down 2, and you leave one of the p's as a p. So it doesn't change, it doesn't hybridize. That p electron that you left alone can make a pi bond with another p electron on an adjacent atom. So that will make a pi bond, which will hold this molecule in place. You can't rotate it. You can't rotate a double bond. And then you'll wind up with 3 sp2 hybrid orbitals instead of 4 sp3s. So that means it can make 3 bonds, and they're all going to be in one plane, all flat. So these are always flat. And that's because you've only got 3 hybrid orbitals. So, for example, if this were carbon, it could make a double bond to one thing like O, and then it could make 2 other single bonds. They're all going to be in one plane, and they're going to be 120 degrees apart. So it's going to be a flat molecule. So S1P2 means you have 3 charge clouds, so you're going to have a trigonal planar shape in terms of the electronic shape. And you could also do this with O, and you can also do it with N. And then SP, again, you start off the same way, but this time you leave 2 p orbitals alone, and you only hybridize 1 s and 1 p. So that means these are sp hybrid orbitals. There's only 2 of them. We've got s1p1, so 1 plus 1 is 2, so we have 2 charge clouds. 2 charge clouds means we have a linear shape. So this would be, basically it could be something like carbon dioxide, like this, where you have C double bond O here, and then that would be 1 sigma bond, and then it would be one of the 2 pi bonds here, and then you have a double bond O on the other side, where this is the other pi bond. So you have 1 pi bond going, let's say, up and down, and you have another one going in and out. Okay, or it could be CO, or other things that have a triple bond. But this one is not as good an example because it only has 2 things in it. And we really prefer to have 3. So this actually turns out to have a lone pair over here on the O and on the C. So really, I mean, this is a linear electronic geometry because you've got, if you call this your central atom, the C, then you've got the O on one side and you've got this lone pair on the other side. But that's not a very good example. But the thing is all right, so for SP, you'll either have a triple bond or you'll have 2 double bonds, okay? So let me say it again. For SP here, you'll either have to have a triple bond or 2 double bonds, and it's going to be linear, and there are going to be 2 things sticking out off the central atom. Either 2 atoms like we've got here for CO2, or a lone pair in another atom as we have for CO. Now for SP2, you're going to wind up with a situation where you have a central atom like this with 3 things arranged around it in one plane like this and like this. The angle would be 120, and these could either be atoms or they could also be lone pairs. So you have 1, 2, 3 things. They're all in one plane. So for sp2, we've got 1 plus 2 is 3, so we're going to have trigonal planar for our shape, for our basic shape here. And it will always be that way for the electronic geometry. Okay, and then for SP3, I don't want to draw it, and I'm running out of room anyway. And the more I try to draw something more complex like SP3, it's going to get harder. But just imagine that you've got 4 things arranged around a carbon like CH4. You could also have NH3 and then a lone pair, or you could have H2O and 2 lone pairs. In all of those, you're going to have SP3 hybridization, because in all of them you still have 4 charge clouds arranged around a central atom. So let me say that again. For CH4, you'd have 4 atoms. For NH3, you'd have 3 atoms, but you'd also have a lone pair. So you have a total of 4 charge clouds around the N. For H2O, you have 2 atoms, the H's, but you've also got 2 lone pairs, so you've got a total of 4 things around the central atom. So H2O, NH3, and CH4 all have SP3 hybridization. Next slide. Okay, so here you can look at these, go over these. I'm not going to go through all these because I think we've already mentioned all of this. Let's go to the next slide. So using the localized electron model for H2O, we're going to have an O in the middle, an H here, and an H here. Let's count the electrons. We've got 6 for O and 2 for the H's. That's 8, and we'll use 4 of those here for that bond, and for this bond we'll use 2 more. Starting with 8, we used 4, so we have 4 left. They can't go on the H's because the H's are full, so they have to go on the O. So we have to put 2 here and 2 here. That's 2 lone pairs. So the O has 2 lone pairs, and it has 2 bonds. That's a total of 8 electrons. So the O has an octet. Now, the localized electron model means valence bond theory. So what kind of bonds are these going to be? These are both going to be just sigma bonds, because they're going directly between the O and the H. So in other words, to get a pi bond, you have to have either a double bond or a triple bond. That's the only way you can get a pi bond. We don't have that here, and we don't have that here, so we wind up with 2 sigma bonds. So these are both sigma bonds. So this one is a sigma bond, and this one right here is a sigma bond. So we have 4 things around this central atom, 2 lone pairs here, and we have 2 atoms, so it's a total of 4. So we're going to have SP3 hybridization. SP3. Now you may say to me, well, that doesn't look like it would be SP3. Well, remember the SP3 needs to have 1 plus 3 is 4 charge clouds, and the charge clouds don't have to be atoms. They can be lone pairs. So when you're doing SP3 and all that, you're dealing with the electronic geometry. Next slide. Next slide. And then we're supposed to do this again for H2CO. That's the way this looks. This is all one plane. This is going to be SP2. It's going to be in one plane. The angles are going to be 120. And we're going to wind up with 1 plus 2 is 3. So let's write a 1 here. 1 plus 2 is 3 charge clouds. So look, around the carbon here we have 1, 2, 3 charge clouds. In this case, all atoms. Notice also we have the same thing here for the O. We have 1 lone pair here, 1 lone pair here, and then a bond here. So the O is also SP2. So notice your clue here is a double bond. Whenever you've got a double bond, you've got SP2, and it will be flat. You'll have 3 charge clouds around a central atom. Angles will be 120, all flat. You would have sigma bonds between the C and the 2 H's, and then you'll have 1 sigma bond between the C and the O, and you'll also have a pi bond between the C and the O that will go above and below the plane. Next slide. So you can read this at your leisure. Next slide. Here's a picture of it. This one is actually for CO. No, this is the same one. Okay, so here, over here on the right are your lone pairs. Here's your sigma bond between the C and the O, and then top and bottom would be the 1 pi bond between the C and the O. Everything else except for that will all be in one plane like this. Next slide. All right, here's a question you may see on the final or on my exam. We're supposed to, without reading the whole thing, we're supposed to find how many sigma bonds and how many pi bonds we have, basically. That's the main point. So sigma equals a certain number, and pi equals a certain number. So pi, let me just get this set up. Okay, so let me give you the trick to this. To count the sigma bonds, you just count the total bonds. So count every bond one time. So if you have a single bond counted, if you have a double bond or a triple bond, you count it once. So it would be like 1, 2, 3, 4, 5, I'm going from left to right, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. So we have 33 sigma bonds, and that's just the total number of bonds. To get the pi bonds, you count 1 for every double bond and 2 for every triple bond, but we don't have any triple bonds here, so it's just double. So just count the number of double bonds. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So each of those double bonds will have 1 pi bond, so we have 9 pi bonds. And that's the answer. That's all you have to do. Okay, so very, very easy question. And then the the hybridization here will all be sp2. Every silly one of these things has, except for the H's, has sp2 hybridization. So all of the C's and the N's and the O's, the O2 has sp2, and if you'll look at every one of them has 3 charge clouds around it. So like the N there at the top right has 1, 2, 3. The O down at the very bottom right has 1, 2, 3. So all of these have, actually that N there that I just mentioned, I just realized actually has sp3 hybridization because it has 4 charge clouds around it. But they're only asking about the carbons, but it also turns out that the O's will be the same as the carbons. They'll have sp2 hybridization. So all of these are going to be sp2, the carbons and the O's, everything except that one N. And so what that means is that this molecule basically is flat. Next slide. So we have 33 sigma bonds, and we have 9 pi bonds. Next slide. So now going to molecular orbital theory, what we would do is we would have to have a little diagram like this, where we have to put in the electrons starting at the bottom and working our way up and putting in 2 in each one of the orbitals. So spin up, spin down, so forth. So if you only had 2, then you would just put 2 there and you're finished. And then this would be the anti-bonding thing up here. Whenever we have either H2 plus or H2 or H2 minus, we would have here 1, and here we would have 2 electrons, and here we would have 3. So if we put either 1 here, or if we put 2, or even if we put 3, we're still going to have a stable species. The bond orders here would be, if we have 1 electron here, we'd have 1/2, 2 would be 1, and 3 would be 1/2 again, because we would subtract 2 minus 1 and divide by 2, so that would be 1/2. It's only when we put in that 4th electron right there that we have 2 minus 2 is 0, which means that we don't have a bond at all, so it wouldn't be stable. So for H, it would be when you have H2 with 2 minus. That means you've got 2 H's that have 2 electrons each. 2 plus 2 is 4, so you put 2 in the bottom here and 2 in the top. Now we use the same diagram for HE, because all we're dealing with here is things that are in the 2s or the 1s orbital. In this case, it's 1s. So we have room for 2 here at the top, and we have room for 2 at the bottom. Okay, so for HE, He2 plus means you've got 2 electrons. So 1, 2, 1 up, 1 down. And then 2 minus 0 is 2. 2 divided by 2 is 1. So this one has a bond order of 1. He2 plus means you've got 2 on one side, which I'm just going to draw this real quickly. So that this He has 2, and this He has 1. So you have a total of 3. So put 2 in the bottom, as we've already done, and then put 1 in the top. So the bond order is 2 minus 1 is 1. 1 divided by 2 is 1/2. So this one is 1/2. but it's still stable because it does have some bonding. But when you have He2, you would have 2 on one side and 2 on the other side. That's 4. So 2 on the bottom and 2 on the top. When you do the bond order, you get 2 minus 2 is 0, and then 0 divided by 2 is 0. So this bond order here, like the one directly above it, the H22 minus, is 0. So it is not stable. So this one will not be stable. The other ones all will be. Next slide. Next slide. Next slide. Okay, so here is the actual diagram that you would use. This one is showing where you have two H's coming together to make H2. So here you notice that each of the H's donated 1 electron. So we have 2, and they both go in that bottom one because it can take up to 2. If you had another one, you would put it here, spin up, and then if you had a fourth one, you would put it here. But if you have a fourth one, then your bond order would be 2 here minus 2 here in this anti-bonding orbital, which is 0. 0 divided by 2 would be 0. So you really wouldn't have a molecule. Next slide. So now let's do this for Li2, C2, and S2. We'll have to go to the next slide. So for Li2, first of all, we don't worry about these things in below down here because that's not the valence shell. All we care about is the valence shell, which is going to be the stuff up here. All right, so lithium is 2s1. We've got 1 lithium on one side in the yellow box here and 1 on the other. So a total of 2. So put 1 plus 1 is 2. Put both of them right there. And then there's nothing left over to go on the top. So what's your bond order going to be? It's going to be 2 minus 0, where I'm saying 0 because there's nothing in this top one, which is the anti-bonding. So 2 minus 0 is 0. 0 divided by 2 is 2 minus 0 is 2, and 2 divided by 2 is 1. So the bond order is 1 for this one, and it will be diamagnetic because it will go through a magnetic field. So remember, dia means through. It's from the Greek. Let's go to the next one for C2. Okay, for C2, again, forget about, and we're only worried about the one on the left. I just put this thing over here to show you that there are different ways carbon can exist, but we're only going to worry about the one on the left. And we forget about this part at the bottom because that's not the valence shell. So each carbon atom will have 4 electrons here, and they're actually correct here in showing these gone, because a lot of the structure will show both the atomic and the molecular orbitals full, and you can't have that. So they've shown these as being empty. This one is empty, and this one is empty because they've been moved over to the middle to make the molecule, the C2 molecule. But there would have been 4. There would have been 4 here, and there would have been 4 here. So 4 plus 4 is 8. So 2 there, 2 there, 2 there, and 2 there. 2, 4, 6, 8, and we've used all of them up. So to get the bond order, we count these 2 here and these 4 here, which is 6, and subtract these 2 because these are in an orbital marked with this asterisk, so they're anti-bonding. So 2, 4, 6 minus 2 is 4, and then 4 divided by 2 is 2. So whenever you've got the C2 like this, it's going to be a double bond. So it's going to be C double bond C. Next slide. Oh, and will it be, before we go to the next slide, it will be diamagnetic, and if you look there, all the electrons are paired, right? All right, next slide. And then when we do S2, we're going to have, first of all, we're going to be in the 3rd row, so we won't worry about things in the 1st row or the 2nd row. It's in the 3rd row. There's going to be 6 electrons on each side, and here they're actually showing this kind of like incorrectly because they're showing both the atomic electrons and the molecular, which, I mean, it's okay to do that. But on the right, we've got 2, 4, 6 electrons in the S on the right, and we have 6 in the S on the left. So we have a total of 6 plus 6 is 12 electrons, which we are going to now start at the bottom down here and put 2, 4, 6, 8, 10, and then when we get up here we have a problem right here because we have 2 left over and we can't put them both in the same orbital because of Hund's rule. So we put 1 spin up in one and 1 spin up in the other, which is okay. To get the bond order then we would have 4, so let me just point these out, 2 here And these two that we put in last are also in anti-bonding orbitals, so we have a total of 4 in anti-bonding orbitals, and count how many we have, if you would, in bonding orbitals. And you should get 2, 4, 6, 8, and 8 minus 4 is 4, and then 4 divided by 2 is 2. So the bond order here would be 2. That's all you have to do for these. You don't have to supply the diagrams. They'll be supplied for you. The other thing we need to look at is this going to be diamagnetic? Well, to be diamagnetic, in other words, to go through a magnetic field, the electrons all have to be paired, but look at the top there. There's 2 unpaired electrons there. Can you see that? So this will not be diamagnetic. It'll be what we call paramagnetic. In other words, if you try to shoot this stuff through a magnetic field, it won't go. It'll stick to the electrodes, or the I should say poles of the magnet. Okay, so this one will be paramagnetic, so it's just like O, which is just above it in the chart. Next slide. Okay, so just another comment since we're done with MO theory. Remember, MO is not hard at all. It's the easiest thing we do. Just count the electrons on the left, count the electrons on the right, add them together, and start putting them into the diagram in the middle, from the bottom to the top, if you have that many, and put them in 2 at a time, unless you get to a thing where you have 2 or 3 orbitals that are right next to each other, in which case you have to put them in spin up, spin up, spin up, and so forth. Then all you have to do is count the ones that are in bonding orbitals and subtract how many electrons you have in the ones that have the asterisks, and then divide whatever number you get by 2, and that gives you the bond order. If you get 1, then it's a single bond. If you get 2, then it's a double bond, and so forth. And you can get half. You can get half of a single bond, or you can get 1.5 bonds, or whatever. Okay, so let's go ahead and move on and finish this. So this is multiple choice. With regard to hybridization, 1 sp2 comes from 1s and 3p hybrid orbitals, and that's wrong. It would be sp3 for that one, not sp2, so we can mark 1 off. It's wrong. Number 2, for sp2, 3 equivalent orbitals are formed, and this one is okay. S1p2 is 3, 1 plus 2 is 3, so we should get 3 equivalent orbitals. Number 3, for sp2, we get 1 p electron remaining as a p electron. That's correct, so that it can make a pi bond. And for sp3, 4 equivalent orbitals are formed. That's also correct. So the answer is going to be 2, 3, and 4. So the answer here is going to be B. Next slide. Next slide. Regarding bond formation, 1, double bonds are formed from 2 sigma bonds. No, it's 1 sigma and 1 pi. 2, triple bonds formed from 2 sigma and 1 pi. No, they're 1 sigma and 2 pi. 3, single bonds formed from 1 pi bond. No, that's 1 sigma bond. And 4, double bonds formed from 1 sigma bond and 1 pi bond. That's correct. So it's 4 only. Answer choice D. Next slide. Next slide. For sp3 hybridization, it involves 4 orbitals. 1 was originally s, 3 were originally p. That's correct. 2, the s orbital moves up, the p orbitals move down. That's correct. 3 hybrid orbitals are produced. That's wrong. It's 4 sp3 hybrid orbitals. S1p3, that's 1 plus 3 is 4. So 4 here is correct. 4 equivalent hybrid orbitals are produced. So 1 is right, 2 is right, and 4 is right. So the answer is going to be E. Next slide. Next slide. According to valence bond theory, covalent bonds are formed by overlap of atomic orbitals, each of which contains 1 electron of opposite spin. We didn't talk about this specifically, but it's true. 2, the greater amount of overlap, the stronger the bond is. True. 3, bonds formed from head-on overlap directly between the 2 nuclei, whether they're sp or hybrid orbitals, are called sigma bonds. That's true. And 4, bonds formed from indirect overlap are called pi bonds. That's also true. So our answer is going to be D, all of the above. Next slide. Next slide. 16, the blending of 1 s orbital and 2 p orbitals produces sp2, and 1 plus 2 is 3, so you would have 3 of them, so it would be 3 sp2 hybrid orbitals. B. Next slide. Next slide. S1P3D2, 1 plus 3 is 4, 4 plus 2 is 6. It will accommodate 6 electron domains. So the answer is going to be E. Next slide. Next slide. All right, this one's a little tougher. The hybridizations in IF3 and IF5 are blank and blank. Okay, so I actually put the drawings in here, but you wouldn't get this on a test. So you would have to do this. For IF3, I and F both have 7, and also for IF5. They both have 7 valence electrons. So for the one on the left here, 1 and 3 is 4 times 7 is 28 electrons you're starting with. You start with 28 and you're making 3 bonds. And that's the reason I say that is because you've got F3, right? So 28 minus 6 would be 22, of which 18 can go on those 3 Fs. So that leaves 2 lone pairs to go on the I. And if you'll look down here, you can see that that's exactly what you have. You have the 3 Fs bonded to the central I here, but you've also got these 2 lone pairs here and here. So that's the kind of thing you would have to be able to supply on your own, and that only comes with practice. So for IF5, which I drew on the right here, I and F both have 7 valence electrons, so that's 6 times 7 is 42. Subtract 10 for the 5 bonds to the 5 Fs, and that's 32, of which 30 can go on the Fs because 6 can go on each F, and that leaves you with 2 left over, and those have to go here on this central atom, which in this case is I, which means we've got an octahedral electronic geometry here. So the hybridization here, you want 6 charge clouds. So to get that, you have to have D2 for this one, D2, and it's really hard to do this, but sp3, it's almost like, okay, sp3. And for this one, to get 5 charge clouds, we have to have dsp3, d1, s1, p3. 1 plus 1 plus 3 is 5. So we need an answer choice that has dsp3 and d2sp3. And the way that he writes them here is he writes it sp3d and sp3d2. It doesn't matter which way you write it. It looks like our answer choice is going to be C here. Next slide. Next slide. All right, the first one at the top, the angles between sp2 are going to be 120 degrees, which we've said quite a few times, right? So sp2 means you've got a central atom with 1 plus 2 is 3 things around it. They could be lone pairs or they could be atoms. So it's going to be in one plane, and the angles here, like between here and here, will be 120, and here's 120, and here's 120, so that's 360, which is what we want. So the answer for this one is going to be B. And then for this one at the bottom, a triple bond consists of, we know what it is, it's 1 sigma bond and 2 pi bonds, so just find that, and that is this answer choice E. So we're going to have B and E. Next slide. And there you go. Next slide. Let's see, we have one more. Okay, so this is really not that bad. I think by the time you go through it 3 times, you should be good on it. So this is the last chapter and the last set of work problems for the test, the exam 3, which I guess we're going to wind up having on Wednesday. So anyway, you can look at these. It didn't take a really super long time to go through this, which is good. So take a look at these, and once you're really, really comfortable with these and you feel like you know them cold, then go ahead, and if you want to, if you've got time, start making up your own problems, or maybe look at some other problems on the internet. And anyway, I'm going to stop this now, and I'll see you in chapter 10.